Hello, welcome to Lecture 24 in the Introduction to Proof series. We're going to be on through section 4.5 today. That's on Russell's paradox. This is the last section in the part on the chapter on set theory. So next we'll be moving on to another section on proofs. So first of all, I think it's worth giving you a little introduction to the personality of the person who's sort of the father of this topic that's in front of us. That's a picture of him. I took that from the History of Math archive. They had several pictures of him, but it's hard to find one where he's not holding a pipe. I think he must have smoked a lot. You don't see that so much these days. He lived between 1872 and 1970. So personally, I was born in 61, so I overlapped with this guy. It's kind of, you know, interesting when you're studying the history of math. You're dealing with people that have been dead for centuries or sometimes millennia. And here's a guy who's famous and fundamentally important to the history of math, who I overlapped with a little bit. The paradox that bears his name, he discovered in May of 1901. So I guess he would have been about 30 or 29 at that point. Outside of mathematics, though, this guy is actually really quite well known as sort of a philosopher and an activist. He was a pacifist, a staunch pacifist. He really didn't believe in war ever. In particular, he protested World War I, which, was actually kind of a popular war. Everybody wanted to have that fight. But he got he was one of the few naysayers there that said we shouldn't do it. And later on, after nuclear weapons were invented, he became a very powerful anti-nuclear activist. As part of his protesting of World War I, he got into trouble, and I think the charge was sedition. He was convicted of a crime and dismissed from Trinity College. And later he spent some time in jail because of that. And during that time, he actually wrote some pretty interesting mathematics. So I've often thought maybe, a nice jail sentence would be good for me too. I'd produce some. No, I'm not in his league. Sorry. Anyway, probably his most famous book was co-written with Whitehead, Alfred North Whitehead, I think is the full name, Principia Mathematica. Now that means the principles of mathematics, right? And that is also the exact title that Newton used for his book where he described calculus. So this is the other Principia Mathematica. I don't believe he wrote it in Latin, as the title might imply. Another thing, really, he was quite famous for in the mathematics world is his defense of logicism. That's basically the idea that all of mathematics can be reduced to pure logic. And it had come under fire. He thought it was the real deal, and he fought for it. I think there's still a little bit of debate on the issue. But anyway, after his time at Trinity, after he left Trinity College, he came to the U.S. for a time, and he was teaching, or had gotten a post at City College in New York. But this was during the run-up to World War II, another very popular war where the people were really quite behind the idea of fighting. So his protesting activity got him in a bit of trouble. There was a lot of people protesting the protesting, and they had a judge declare that he was morally unfit to teach at the college, so he had to leave. It's hard to say. I mean, different people have different political stances on war and stuff, but I think morally unfit is a kind of a strange way to put it. He's somebody who did have very strong ethics, great morality, and he stood up for his morals. What he believed in, he was willing to go to prison for. In any case, he was later vindicated. Amongst many other awards, he got the Nobel Prize for Literature in 1950. And there aren't a whole lot of mathematicians who've won Nobel Prizes. There's no Nobel Prize for math. There is a similar prize called the Abel Prize. It's given away by the King of Sweden. But the original Nobel Prizes, I think Nobel was the guy who invented dynamite. He was a very practical-minded guy, and he didn't think of mathematics as something that was of particular use to humankind. He thought of it as, well, it's a language, I suppose, that a lot of science needs to be done in, but he concerned himself with the scientific products that people made. So that's what the prizes were for. There's also something people call the Nobel Prize for Economics, but that's actually not a Nobel Prize. It was another add-on that the Swedish government put in. So then quite a number of mathematicians have won that. Anyway, let's push on. In 1955, he teamed up with Albert Einstein, which, that's a pretty impressive person to collaborate with. Einstein originally was a promoter of nuclear weapons. He was personally Jewish. He saw what the horrors that were going on in Germany were like, and I mean, he had to flee Germany himself to come to the United States because of anti-Semitism. So he was one of a few scientists who signed on to a letter to the President of the United States at that time, and it resulted in the Manhattan Project and the eventual development of nuclear weapons. He later very much regretted that choice. He saw the potential for destruction, and so he joined with Russell to write this manifesto that basically said human beings really ought to just hang up these particular weapons and completely eliminate them. So in the piece I was reading on the History of Math archive, it mentions two different times when he was imprisoned for his various protest efforts. I suspect that he may have been imprisoned more than that because he did seem to have this courage of his convictions. But at least twice, or two times are mentioned, and the second time he was aged 88. This was for his anti-nuclear work. So I don't know, I'm kind of impressed by that. Well, let's get on to the math of it. The set of all sets, that's the section title here. A simple question, really. Can a set contain itself? Now, if I mean contain in the subset or equal sense, of course it can. Every set contains itself that way. But this is as an element. Can a set be an element of itself? And, well, if that's allowed, then you get a sort of a pathological situation that you probably don't want to have around. Let's take a look at this. You get this is a good way to say it. You get an infinite regress if a set is in itself as an element. So here's an example. Suppose A is the set that contains the numbers 1 and 2, but then kind of a copy of itself, A, inside of there. Well, look at what happens if you expand that. A is 1, 2A, but then that A can be expanded into a 1, 2A, so you get 1, 2 combo 1, 2A, and so on and so on and so on. You get, obviously, it'll blow up, right? It'll become an infinitely long expression, and you'll never have anywhere to write those final infinitely many part curly braces on the end. It'll get weird. So we don't want that. So this is what mathematicians of the time, around 1900, chose to do with set theorists in particular. We'll do set theory within the set of all sets, but the set of all sets that don't contain themselves. And I believe the term at the time was amenable, but I couldn't find any reference to that. I thought that I had once read that they called sets that did not contain themselves amenable, which is a nice word, and it means that you're okay with doing something, right? In any case, we don't need to have a name for them. We'll just talk about them. On the surface, whenever you do something in math, you want to concern yourself with, are we defining something that's known with precision? Are we making something that's well-defined? I just noticed something. I used well-defined with a hyphen up here and well-defined without a hyphen down here. I believe it's supposed to have the hyphen, so maybe I'll fix that before we have to load the slides. Anyway, is it well-defined? Well, the membership criterion would be the open sentence, X is a set. And I think it's pretty clear that, we know when we're looking at something, whether it's a set or not. Right? Can you tell if you're looking at some expression or somebody names a thing, can you tell whether that's a set or whether it's not a set? Well, I guess there's some gray area. You could say, look at me. Am I a set? ordinarily you wouldn't think that, but if you looked at me as a biologist, you might think about the set of all those cells that are agglomerated into that human. It seems like most of the time, though, we'd be able to say, that thing's a set, that thing's not, and we'd be very precise about deciding what was in the set, the set which would have membership criterion P of X. So, amongst those things that are sets, surely you can tell whether they contain themselves or not. Just look. If they contain themselves, it'll be obvious. If they don't, then that'll be equally obvious. So that seems good. Well, that's where Russell found the problem, though. He realized that there was a way to get at something there that caused a real furor. Now, this actually, I think, might be surprising because I don't know if such a fundamental flaw in mathematics were discovered today, whether there'd be much of a deal about it. But at the time, people were excited about this. This was big news that a mathematician had found something that essentially showed the foundations of mathematics were shaky, that a lot of math didn't make sense anymore. And the barber paradox was introduced to try to explain to people fundamentally what was going on, what Russell had found, how it worked. I don't know, and it may not be knowable at this point, whether the barber paradox existed prior to Russell or whether it was invented strictly to describe what was going on with Russell's paradox. But in any case, it's viewed as sort of an easy, light version of Russell's paradox. So first we'll look at that, and then we'll go on to the full strength thing and deal with Russell's paradox itself. So yes, the paradox in the barber paradox, it's essentially the same paradox that's at the heart of Russell. But yeah, people think of it as easier. Though to a modern listener, modern reader, it is going to sound a little odd. So just remember, this is coming from 100 years ago. I like to think of this I see things like this in movies where there's these little towns in the West, with one dusty street running down the middle and maybe a couple of dozen occupants, maybe 100 at max, small places. And cowboys would occasionally come riding in, I should say, bring their horses in off the range, and they would go to the barber and get cleaned up before having a big night on the town. Well, that's the image I have. The other thing I got to mention, because we're going to be talking about this who shaves the barber question, you're probably familiar with razors as we see them today, Schick razors that have a nice plastic coating. The blades are in there in a way that it's really hard to hurt yourself with. Frankly, I shave my head almost every morning, and I don't have to take any special care not to cut myself. But the razors these people needed to use, it was long before plastic. So they had blades that usually collapsed. They folded them into a sheath. But the blade was a straight piece of steel that was literally razor sharp. You took this edge and you scraped it across your face or whatever you were trying to shave, and if you slipped, you would cut a gash in yourself. If you moved, instead of sideways, if you moved this way, you could really damage yourself. I'm not talking like the nick that some people get shaving today where you have to put a little piece of toilet paper on it. I'm talking like, you got to go get stitches. So they were dangerous. In fact, there were people who carried straight razors as weapons. They're very uncommon today, fortunately, because they're the sort of weapon that could do quite a lot of damage to somebody. So here's the paradox. That's the setup. In a small town, the barber shaves all those men, and only those men, who don't shave themselves. So the barber shaves you if and only if you don't shave yourself. That's the setup. And then there's this question that I titled the slide with, who shaves the barber? Well, who does, indeed. Okay, so today we would most likely resolve this by saying, well, maybe the barber's a woman. That didn't even occur to people back then. Being a barber was a completely male-dominated occupation. There weren't any female barbers in 1900. I would be surprised if there was even a single one. Certainly, yeah, it would be amazing. So that resolution didn't bother people. The next thing people say is, well, maybe the barber grows a beard. He doesn't shave. But if he doesn't shave himself, What the setup said, that we read that part that was in bold, and it seemed to make perfect sense. What that says is if he doesn't shave himself, then he's one of the people he's supposed to shave. So he can't grow a beard, but then he also can't not grow a beard, because if he does shave himself, then he's one of the people he's not supposed to be shaving. You see how that causes a problem? We go round and around in a circle. So we're going to let P of X be the sentence. X shaves himself, and the barber is B. So we get P of B implies not P of B, and not P of B implies P of B. Or, to put it another way, P of B if and only if not P of B. And that is a contradiction. So let's think about why that's contradictory. If a statement implies its own negation, that first part, P implies not P, that'd be okay. That just could be that the statement is false. So even if it's true, it's false. But if you've got it both ways, the statement implies its negation and the negation implies the original, you get stuck in a loop. You go in an infinite loop. So I have an example here of that. There's kind of a classic thing. You take a sheet of paper, and on one side of it, you write, what's on the other side of this paper is true. So then somebody will flip it over, and they will find on the other side the sentence that says, what's on the other side of this? Let me move this where we can see it better. What's on the other side is false. And then you go, well, wait a minute, what's the thing on the other side say? You flip it over again. Oh, it tells me that what's on the other side is true. So it's true that this is what this is saying is true. Okay. So that means the statement on the other side is false. So wait a minute, this is a lie, but that means the thing on the other side is not true if this is a lie. So the thing on the other side is not true, but this is saying that the thing on the other side is false. So if this is not true, that means, you see where I'm going? That I get stuck doing this over and over and over again, constantly flipping it back and forth, getting 9 layers deep, or infinitely many layers deep in this thing that's ultimately a contradiction. So one way to think of this problem we run into with Russell's paradox, or with the barber paradox, is you go into a loop. That's fine, but now that we've done some formal logic, we can say this a different way. We can just use logical equivalences and immediately see this is equivalent to a contradiction, a statement that is simply never true. So how does it go? You're given that P implies not P and not P implies P are both true. That's the given sentence. I just convert those if-thens to disjunctive form, to an or sentence. So do you remember how that works? You replace the if-then symbol with an or, and you negate the thing up front. Not P, so this becomes not P or not P, and the other one becomes double negation. I guess I should have said I used that in here, but not P becomes P ored with P. So disjunctive form of both of those conditionals. And then do you see that we can throw in idempotence? Sure. Not P ored with not P, that's just not P. P ored with P, that's just P. So we've got not P or P. That's one of our rules, right? Complementarity. If you say a sentence is anded with its own negation, one side of this or the other is false. So the and will be false. You get an always false sentence because of the complementarity rule. So yeah, a contradiction. All right, so I hope that leads you to start thinking about the right kind of issues while we talk about the real Russell's paradox. That one's just a warm-up. So here goes with the real one. First, it's concerned with this set we talked about before, the set of all sets that do not contain themselves as elements. Let's call that S. Right? S is going to be the set of all sets that don't contain themselves as elements. Here's a formal definition of it. S equals the set of all A such that A is a set. It's a set of all sets, right? So the A has to be a set, and A is not an element of A. That's a great formal definition of the set we're after. Really doesn't seem like that there could be any flaw in that, does there? Okay, but there's this inconvenient question that they asked in the barber thing. Who shapes the barber? What's the Russell's paradox version of that, it's this. Is the set S an element of itself? In other words, apply the same condition that's in there in the definition of it to itself. Self-reference is often a great way to come up with a paradox. So is S in S? That's a great point that slide makes. There's only two choices. Either it's in itself or it's not in itself as an element. It's either an element of itself or it's not an element of itself. But here's the issue. If it's in itself, then it has to satisfy the membership criterion for itself. And the membership criterion, let me just back up a second, was these two things. It needs to be a set. I'm not going to worry about that, but it also has to not be in itself. So if S is in S, then it says that S is not in S. We've got a P implies not P. If it was just that, it'd be okay still. We wouldn't have a paradox. But if it is not in itself, then what does that tell you? Well, it in fact does satisfy the membership criterion for S, which I don't think I need to go back again. We just saw it. A is not in A. So S is not in S. So it satisfies that. That means it is in S. It's in itself because it's not in itself. What? What we've got there is a sentence that looks like P if and only if not P. Actually, I broke it into two sentences, but those are connected with an and. So P if and only if not P, where P is this logical statement, S is in S. That's a paradox. That's a contradiction. So how do we get out of this stew? How do we resolve this issue? Because we're pretty much screwed at this point. Set theory is the foundation of all mathematics, and set theory has a nasty contradiction hidden in its foundations. Just talking about the set of all sets, which seemed like nobody could complain about that, led us to this weirdness. And if you have a contradiction in amongst the sentences that you accept as true in a logical theory, there is a statement called the principle of explosion that says, from a contradiction, you can deduce anything whatsoever. Any statement at all can be deduced from a contradiction. I hesitate to recommend this to you, but there's an XKCD cartoon about the principle of explosion. You can just Google that. I don't want to put it up because it's mildly prurient, but it's not that bad. So if you're curious, Google it. I'm not going to endorse. Yeah, I'm sort of partly endorsing it by saying it's funny, and yet I don't want to show it. So Russell himself developed a way to resolve the problem. He developed something called type theory. And the essential idea is that sets and their elements are of different types. So if a set and its element are of different types, the idea of a set being in itself doesn't even make sense, because the elements have to be a different type than the set itself. You just couldn't even talk about this situation. Kind of defining your way out of the situation that became problematic. Now, type theory didn't really catch on that well. A lot of people had complaints about it in multiple directions. Some people thought it imposed too strong restrictions, others that it was too weak. But that was one way to do it. The logicians have developed other methods, but I think for the typical working mathematician, an approach that works pretty well and won't leave you concerned too much about the foundations is just, let's demote the set of all sets. It's not a set anymore. Let me back up one last time to that definition of the set of all sets that don't contain themselves as elements. It had two things. The things need to be sets, and they need to not be elements of themselves. Well, if you're not a set, then you fail on this one. Back to where we were starting. So if you don't, sorry, let me think this through. If you demote the set of all sets to merely be calling a collection, not a set, then it fails that first part of the membership criterion. So it doesn't matter. You never see. If you ask, is S an element of S? The answer is no. because it's not a set. Well, what does that say, though? Really, the difference we used, the line we drew between sets and collections was that we knew what were in sets. Their membership criterion were decidable logical sentences. So we knew that if you ask me about a particular thing, I've got a test that tells me for sure, is it in the set or is it not? What we're saying here is that's not true for sets. We may not know whether a thing actually is a set or not. So yeah, that's just a restatement of what I just said in words, in speech rather than in writing. While S may or may not be a member of itself, it's not a set, so it fails the first part of that membership criterion. Well, that brings us to the end of the slides for today, and my suspicion is that was a little bit of a short session. So I thought it might be nice for us to end this session with some sample type questions you might see on a test about set theory notions. So this is actually some stuff from one of my own exams from summer, quite a few years ago now. But I just thought it'd be nice to give you kind of an idea of the sort of things that you might run into in a set theory testing situation. So the first one here is pretty straightforward. It's basically write a two-column proof of a set identity. Is that one going to be easy enough to do? Let's see, we've got A intersected with B union C bar, and there's parens around that, the three of those things, right? And then that's intersected with B union C. And is that in fact the same thing as just A intersect B? Well, I believe it. So let's start by just copying out the first thing. We have A intersected with B union C bar in parens intersected with B union C. As per my previous advice on this, you want to usually start with the more difficult side. So that's our given statement. And we're going to work from there until we get to A intersect B, hopefully. Well, I don't know if you're noticing the B union with something and the B union with something here. I feel like we might be able to suck B out of that with the distributive law, but they're currently not grouped together. So let's first reassociate. You notice that this symbol and this symbol are both intersections. And the parentheses can be moved from around the first intersection to around the second intersection. So you get this. A intersected with parentheses of B union C bar intersect B union C. Whoops. Need some white out. Let me just scribble that out and write a union sign under it. Is that more or less clear? Do I get the right number of parentheses? This one is ending with that one. Yeah, okay. So what did we use? That was the associative law. Now, personally, I don't tend to write these things all the way out. Ask your instructor what their preference is, right? If you're doing this with an instructor, they may prefer that you write things out. I go with abbreviations, it's fine. Well, why did I do that? I was sort of looking ahead, seeing that I had B unioned with stuff here. So what rule were we using if we factor B out of those two expressions? That's the distributive law. So inside this big parentheses, we're going to have B unioned with C bar something C. What symbol goes between C bar and C? It's the intersection that was there. Doing the distributive law in reverse, factoring out, sometimes is a little harder, but let's just label that dist. I think that's good enough. Does that look like an R? Now we're getting somewhere, because what's C bar intersect C? C bar intersect C, there's nothing in common between a set and its complement. So that thing's an empty set. So what we have here is A intersected with B union with an empty set. And what rule did I just use? That's complementarity. Fine. Then finally, it's just unioning an empty set on with B doesn't really add any new elements to B. You still get B, the identity law. Right? So here we get just A intersect B using the identity law. And that's where we wanted to be. So there you go. That's not too bad. Um, Depending on personal preference, professors will typically not give you two-column proof things that are going to go past 5 or 6 deductions. So if you find yourself at deduction number 11, there's a good possibility you went off in the wrong direction somewhere back on the beginning. And personally, that's all I would ever really put on there. But I see it all the time. I've got something that I know you can get to the conclusion with 6 steps, and people have filled up 2 pages. So just word to the wise, if you find yourself filling up more than 1 page, it's likely that you missed a step early on. Okay, another exam problem. This was number 7 from one back in 2012. Just a question about understanding the subset containment symbol versus the element symbol. So A is the set. It's a fairly complicated set here. It's got letters A and B. It's got numbers 1 and 2. Then it's got a set with the numbers 1 and 2 in it. And finally, it's got a set that contains a set with the letter C in it. Right. So a lot of stuff there. Is the empty set contained in A? Of course it is. That's always true. The empty set is contained in anything, because to check that it's contained in that other thing, you just have to look at all its elements and see if they're in there, and you're already done. There's no elements to check, so that's easy. Is the set containing C an element of A? Well, yes, it is. Maybe I should indicate the top level commas in this set. At those. And one of the things between the last top level comma and the final ending of the set brace is exactly this, envelopment of C with 2 curly braces. So yeah, that one's true as well. Is it true that the set 1, 2 is a subset of A? For that, rather than an element question, this is a subset question. You have to check that both of these elements are in there. Now, if you come up here and look at this, that's the set 1, 2. And that's not right? Because that set braces around 1 and 2 hides the things. But there's another place where 1 and 2 appear right next to it. And there they're sort of naked, right? They're in between the top level braces. They're in between the top level commas, excuse me. So yeah, that is a true sentence. Gosh, I hope these aren't all true. That would be boring. How about this? The set with A and B and the set C, is that contained in A? Well, again, the trick when you're doing containment is to look at each one of those elements and see if they're in the set that you're being asked about. A and B are, but the set with C is not. It's the set with C. There's a double set of French braces around that C. So this one's false. Can we see this thing? The set, that double braces around C, is that contained in A? Now we're in trouble in a different way. If this were to be contained in A, that would mean the set, just a single set of braces around a C, would have to be an element of A. And there is no such thing. We've gone off the top of the page, but do you see any C's in here that just have a single pair of French braces around them? Yeah, me neither. So this is false. Probably this one is false too. Is 1, 2 an element of A? I don't remember seeing it. Oh yeah, it is. How about that? 1, 2 is right there in between top level commas. Okay, so a little 2-column proof, that was easy enough. Here's just checking that we really understand element versus subset. The next one is just checking our ability to see if we remember what Russell's paradox was really saying. It's interesting. In this test, I actually used the terminology amenable. to talk about the sets that don't contain themselves as elements. At least at one time, I was convinced that that was the terminology in use back in the day, back in 1900, but now I'm not so sure. So the contradiction, it says, was S in S implies S not in S, and S not in S implies S in S, which is true. That's the contradiction. But what it actually asks us to do is give us a precise definition of S. So what is the set of all sets that don't contain themselves as elements? I think I can remember that. Let me just say it was S is going to be the set of all things A, such that, first of all, A is a set, and second of all, it's not in itself. More or less a test on just your memory. Do you recall the definitions of the things that we were talking about? Okay, so that's 3 questions on set theory. Oh yeah, no, there's a 4th. I thought I had. Okay, so here's a collection of 4 sets, and we're asked to go to figure out the relationship between the following 4 sets. So, and it says do it with Venn diagrams. Okay. So what is A? First of all, A is the x in the integers such that 2 divides x. That's easy. That's the even numbers. I'm just writing a note to myself to sort of think about what that is. X in z such that 3 divides x. I like, it's silly, but I like to call that the 3 even numbers. So since I'm just writing a note to myself, that's fine. 3 even is like the 3 version of even. Get it? Okay. How about the set C? X in z such that 6 divides x. Well, that's interesting. That's actually both, right? It's going to be divisible by 2 because 6 is divisible by 2, and it's going to be divisible by 3 because 6 is divisible by 3. This is the things that are both even and 3 even. Just think about the. Maybe it was a good idea for us to write out some of these sets. A is, it'll be -4, -2, 0, 2, 4, and then dot, dot, dot out that way. It's infinite in both directions. B, that's the 3 even things, the multiples of 3. So dot, 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 it'd have minus, let's go -6, -3, 0, +3, +6, dot, dot, dot that way. And C, that's actually, well, if I do the same pattern of showing like 5 things in the middle, it would go -12, 6, 0, +6, +12, and then on forever in that direction, multiples of 6. What about this set D they're talking about? These are the things where 2 does not divide the number and 3 does not divide the number. And well, let's take a second and at least get A, B, and C on here. We'll do a Venn diagram. Try to make it a nice big one. Set A is that. Set B is like that. And I think it's clear to everybody that C is what's inside of here. Let's shade that the intersection. C is equal to A intersect B. But where is D? Well, D is, it says it specifically, it's the things that are outside of A, because, can you see it at the top of the screen there? 2 does not divide x. So things that are not even, odd numbers in other words, and not divisible by 3. That means it's the intersection of the complement of A with the complement of B. What set is that? It's outside of A and at the same time outside of B. So things that are in B won't be in it. Things that are in A won't be in it. Things that are in both of them certainly won't be in it. It's all the stuff outside. So maybe I can try to stripe it or something. This is a little hard to draw, isn't it? This is this is not our universal set. The universal set would include the stuff inside of here, but rather it's the stuff outside of both A and B. So D is striped, I guess I'll call it. Now there's one last thing on this sample test that I was showing, but it was an extra credit thing. I'm afraid I trimmed off the edge of it too. It's one of those knights and knaves puzzles. So I think it's worth showing to you, and I'll leave it to you to try to solve this one. A, B, and C, Abraham, Balthazar, and Cincinnatus, are these individuals we run into. One is a knight, one is a knave, and one is a neither. So knights are as before; they can only make truthful statements. The one that's a knave will only make false statements, but a neither, it's like a real human being. They can sometimes be right and sometimes be wrong. The statements they make are: Abraham says Cincinnatus is a knave, Balthasar says Abraham is a knight, and Cincinnatus says I am a neither. Who's who? That's your job. All right. Well, that still is going to leave us a little bit short, I think, on this lecture. But sometimes you win, so there we go. Thanks for sticking it out, and we'll see you next time when we're going to start looking at mathematical induction, one of the sharpest tools in the mathematician's toolkit. So have a great day.